Hi, welcome to Real Learning Center. Today we are going to talk about laws of motion. The laws are what makes something move, what causes motion, and what are the laws that govern motion. That's what we are going to discuss today. And this is a series which has about 6 sessions and basically 6 videos. The first one being what causes motion. The second one being Newton's laws. Starting with the first law, second law, momentum, and then goes to Newton's third law, and finally collision. These are the things that we are going to basically discuss, and this video is about what causes motion. So let's start with a very simple day-to-day understanding of what causes motion. So let's look at the scenario here. Okay, if you keep on pushing some cart, the cart keeps on moving. If you keep on pushing a cart, it keeps on moving. So if you keep on pushing something, it will keep on moving is one understanding that we have. Okay. Now, is it possible that this understanding can be basically expressed in some language of physics? Most often we actually talk in common language. If you push something, it will move. So what if we want to express the same thing in the language of physics? So it says, if you continuously apply a force on a body, it will continue to move. If you continuously apply a force on a body, it will continue to move. Just observe. Now we are also going to learn how to use language of physics. So when you say pushing, you might always also want to say what happens when you pull it. So in order to basically take care of both push and pull, we use this word motion. Rather, we use this word applying a force. If you apply a force, either push or pull, it will basically cause a body to continuously move. So that is one statement which we can make about motion. But let me put this in another sentence and see whether that makes sense. So what we can say, for example, is if something has to be in motion, there has to be some force which is continuously acting on the body. Okay, now the question basically is this a correct statement? Okay, if we say, if something has to be in continuous motion, there must be a continuous force acting on the body. This is not same as saying if you continuously apply a certain force, a body will continue to move. Okay, this is slightly different. Okay, it's kind of what we call converse. And is this true? It looks like true. Let us go and see whether it is true. So let's now examine both these statements. Statement number 1 and statement number 2, and see whether they are really true. Okay. So let's look at a scenario here. So what you see here on the top is, as you all know, it's a pulling the rope on both sides. Okay. So when you pull it like that, if you take each individual, each individual is actually continuously applying force. Each individual is continuously applying force. If you apply force continuously, there has to be a motion. But both of them are standstill. So what about this? Somebody is pushing a huge rock, hoping to basically make it fall. Okay. Will it move? So that is the question. Now in both these scenarios, if you see, is there anything that is common? Do you see any commonality between these situations? So one is 2 people are pulling a rope, the other one is somebody pushing the rock. Okay. So you can very clearly see that in both the cases, opposing forces cancel each other and net force is 0. In the sense that 2 people are pulling, and if you add up algebraically, in the sense that one pushes that way, one pulls that way, another pulls this way, they cancel each other and there is no net force on the rope. Here you can see, in the second scenario, it is the same thing. It is just that nobody is pushing from the other side of the rock. It is the friction between the rock and the floor on which it is standing, the mountain on which it is standing. There is a friction between these two, and that friction is so high that it is actually exactly opposing the amount of force that you are using to push it. So those two cancel each other, and hence there is no motion. So our original statement, statement 1, that is some force is continuously being applied, then there will be a motion is wrong. And we need to basically modify that. So science in physics basically it is all about making sure that you make accurate statements. So let us see, can we make a better and accurate statement on this? Let's see that. So the statement that we can however make now is, if you continuously apply a non-zero net force, a body will continue to move. So what does it mean? So we are now saying, we just modified that. If you continuously apply force, we remove that and put there, if you continuously apply a non-zero net force, so there may be many forces acting. If you add all that up, and if they don't cancel each other, if there is a net force that is remaining, which is not a zero force, then it will move. Maybe that is a accurate statement. Now, let us see whether we can actually look at the second statement and see whether there is any flaw in that, or is it a good statement. Okay. What was our second statement? Let's examine that. The second statement is, something has to be in motion. There has to be some force which is continuously acting on that. That is the statement that we are making here. Is this something right? Looks right though. So let us see a scenario here. So watch this. A game of, in the game actually he is throwing the ball. Okay. So when he is throwing the ball, you can clearly see that he is applying force. And he is throwing the ball. But after that, if you watch the ball moving, you can clearly see that when the ball is moving there, if you take that scenario and ask the same question, if something is in continuous motion, there must be a continuous application of force. That seems to be wrong. Nobody is applying the force there. The ball is still moving. So our statement that if something has to be in continuous motion, the ball, the force has to be continuously applied. Seems wrong. So what do we do? How do we modify this statement? What is really happening? So maybe we can say something like this. We can say that the ball will be in motion if somebody applied a non-zero net force, and then it will go for some time. Like we can say, for example, if you apply a non-zero net force on a body for some time and then remove it, the body will move for some more time and then stop. Can this be our law of motion? So can we say, if you apply some non-zero net force on a body for some time and the body will move for some more time and stop? Can this be a law? I mean, physicists basically will not agree that it can be a law, because there is a lot of uncertainty here. How much is that some time? How much is that some more time? How long it is going to be in motion? We want to be accurate when we say something. So, a lot of people actually try to define when the body will keep on moving. This is not a question that has cropped up today. This is a question that has cropped up years, thousands of years back. And people kept on answering the way they think is the right answer. Okay. So let us say who tried to answer this first. But there is this guy who you can see is quite famous. I mean, people know about him. His name is Aristotle. He was there more than 2000 years back, 2300 years back. And he had this question. And when he had this question, he answered it in a particular way. He said that it requires a force to make an object move in the unnatural manner. What is the meaning of unnatural manner? Now, in his point of view, there are certain natural movements. So he at that time did not, the people did not know about the gravitation and things fall because of the Earth's gravity. These things were not known. So he said that there are different kinds of material, objects, and he named them in 4 different categories, like earth, fire, air, and water. So 4 different objects he named. Out of that, he said each one of them have certain kind of natural motion. Like stone, for example, is kind of an object called earth, and it has a natural motion of falling down, whereas air has a natural motion of going up. So that was his thinking. And he said that, so if you take any body, okay, if you want to keep it in natural motion, in unnatural motion, which is against the natural motion, then you have to keep on applying force. In nutshell, he said basically, in summary, he said continuous motion requires continuous motion. So you must be continuously applying force to have continuous motion. Okay. And the interesting part is that he said it around 2,300 years back. And people actually questioned him a little bit, okay, saying that is this always true? Is there an exception to this statement? So they asked him a question, and let us see basically what kind of an answer he gave. Okay. First of all, let's see whether you agree with Aristotle. Do you agree that continuous motion requires continuous force? So let us see. So who is this Aristotle? Okay, first let's look at his abilities and what are the things he did. He was one of the greatest scientists come philosopher, whatever you can call those days. Okay. He studied on various subjects. Things like epistemology. I don't know whether you've heard about it. Epistemology is about studying about knowledge. How do we acquire knowledge? That kind of thing. So then he studied geology, a lot of it. Physics, metaphysics, which is somewhat physics but slightly more than physics. And then you have biology and medicine. He had his theories in biology. Lots of things he has done in biology. And he worked on psychology and some philosophy. All that is the areas in which he worked. He wrote lots of books. And one of his, he is known for one other thing. He was actually guru of Alexander the Great. I mean, who doesn't know about it? So he was the guru of Alexander the Great. So Aristotle was such a great guy. He did so many things and he made some statements, and we are only taking his statement from the laws of motion. Remaining we will touch upon some other time. Okay? So now, however, there were some objections during his time also for his question. So he was saying that objects actually move, keep on moving only when there is a continuous application of force. Now you see this guy who is actually, this lady who is throwing up, his fighting arrows, with arrows. So if you see here very carefully, force is applied only once in the beginning. And how can the arrow move after it leaves the bow? While applying the force, you applied the force here, you pulled it and left it, and the arrow keeps on going. Now the question basically is, why it is going? Nobody is applying force, it's still going. So people ask this question. If you are saying that the force is needed to keep somebody in motion, now in this case the arrow is moving and nobody is applying force. How is this true? So Aristotle gave an answer to this. Okay, let's see how interesting is the answer. His answer was, the arrow when it moves, it creates some vacuum behind itself while moving, and the surrounding air rushes in and pushes the arrow forward. Is it a convincing answer? Do you believe in this? But you must be surprised that people actually there believed in it and they liked his answer. And when they liked this answer, how long they liked this answer? And nobody questioned it for the next 1950 years, 1950 years. Nobody questioned statement. Everybody believed that what Aristotle said was right. And Aristotle cannot be wrong because he's such a great guy. So they all believed. For how long? Think about it. It's almost like 2,000 years. Nobody questioned it. But after that time, there was one guy who questioned it. Okay, so let's fast forward ourselves to the 16th century AD. Okay, there, it's almost 2,000 years later, after Aristotle made his statement, one guy who actually did not agree with Aristotle. So he said that that's not true. What is that guy's name? His name is Gelileo Galileo. You can see he is actually the one who did lots of work on physics, and he kind of made his own telescopes and he watched lot of planets and all. So this guy actually did not agree with Aristotle. Okay. So let us see what is this guy, what did this guy say? What did Galileo say? Okay. So Galileo was famous for one more thing. Before Galileo, there was another guy. Okay. So we will just talk about that scientist in a minute. And before that, let's understand what is this geocentric theory. Okay, Aristotle had put forward this theory, saying that Earth is at the middle of the whole universe. Okay, and the planets and stars and all of them and the sun, everything goes around the Earth. That was called as a geocentric theory. Okay, and he just put forward that theory, but one who perfected that theory was Ptolemy. Okay. Ptolemy actually worked on this theory and did all the calculations and everything, and he showed very clearly that Earth is at the center and everything else is moving around the Earth. And when he has to do that, he had to do lots of observations. He did actually years together observations of various planets in the sky, and he wrote down on the drawing sheets basically how they had to move on all that around the Earth. Okay, if you can see clearly how things have to move for his theory to be right. Okay, we can see how the things have to move. Okay, you can see very clearly. In the center there is Earth, and sun going around the Earth, and you can see that lots of other planets are going around, and you can see that they are actually forming various kinds of shapes, not just proper circles. So in order to basically prove his theory, we have to accept that things go around like this in various different kinds of shapes around Earth. See, they form some kind of a small circles there, and they keep moving around. So he proposed that this is how things move around Earth. But there was another guy who came again many years, in the 15th century or so. His name was Copernicus, and he came and changed everything. He said that if you just consider for a minute that actually Earth is not at the center and the sun is at the center, then you can see that the movement of all the planets is so beautiful circles. You don't have to consider all that different kind of patterns. You can see that it just goes around in nice circles. And he said that this is possible. Yeah, it's possible that sun may be at the center and other things are going around, planets are going around the sun. And this theory is called as heliocentrism. Helio means sun, sun-centrism. And people kind of dismiss this theory, a lot of people, because Aristotle cannot be wrong, Ptolemy, there are a lot of observations, everything, and sun, how can it be at the center? We are the people on the Earth and we have to be at the center. That kind of thing. Okay. However, our Gelileo actually believed very strongly in heliocentrism. He said that sun is at the center and not the Earth. And he even showed through telescopes that around the Jupiter, what goes around is Jupiter's moons. The Jupiter's moons are going around the Jupiter, not around the Earth. So something else can be at the center. So he showed all that. And he was prosecuted and jailed till his death for believing in such a theory. Those days it was not such a big freedom was not there for people to believe in whatever they wanted. He not only believed, he propagated that theory very vehemently. He said that yes, heliocentrism is the correct one. So he was actually prosecuted by the Pope, and he was jailed till his death for believing in a truth called heliocentrism. So that was the story of Galileo. Now, getting back to Galileo's view on motion. So let's get back to the same question. Galileo very clearly says that force is not at all needed to keep a body in motion. Okay, force is needed, of course, to start the motion, but he said that it is not needed to keep the body in motion. And he conducted an experiment and developed a logical argument to prove his theory. During those days, it was important to prove through logical arguments. He came with this quite an interesting argument and an experiment to prove this. It requires some amount of logical thinking to be able to understand this. Let's see whether we can get this experiment, what he did. Okay. Let's look at his famous inclined plane experiment. So what he said was that he made one inclined plane like this. Okay. So a ball is here, and if we actually drop the ball from there, then ball will move like this. And we know very well that the ball will almost go to the same height from where it was actually dropped. The same height. Okay. But will not reach the same height. It will be slightly lesser. Okay. But however, if you take this inclined plane and polish it nicely, so that very less friction is there. Once you do that, it will go very near to the more and more you polish, more and more it goes near to the original height. So he kind of concluded that if he had made a very smooth, ideally smooth surface, it might even reach the height. Okay, and while reaching that height, it has traveled this much of distance. You can say how much distance it has traveled. Now he changes the experiment a little bit. He said that I will actually make this a little same height I'll keep, but make it a little more further. Okay. And now when you leave the ball, it will again go almost to the same height. And while doing so, will traverse a longer distance. Okay. Then if you make it even bigger, then it will actually go to again try to go to the same height and traverses even longer distance. So at this point, actually, it took off. His imagination went into the next level. And he said that, now, assume that I make it extremely smooth so that there is zero friction. And I will make this inclined plane slightly different. I'll make it like this. Okay. Where it will keep on traveling till it reaches that height. But you know very well that it will never reach that height. And hence, it will keep on traveling. That was an inductive logic which Gelileo used. He said that ball is going, and never stop. Is force acting on the ball? No. But logically we know that it is going. Because we have given an infinitely smooth plane. And it has been given a start. Some little bit of force coming down. And now it is keeping on going and there is no force acting on it. And from this he concluded and he urged people to understand that there is no force required to keep some body in movement. It may be required to start the movement or stop the movement and all that, change the direction of the movement, but there is no force required to keep some body in movement. So this is actually today somewhat easier to understand. Whereas in his days it was harder to understand because nobody had ever experienced what happens if you go to space. So they were all their experiences around the earth where gravitational pull and air resistance and friction on the ground, everything is there and it cannot be zero. Okay. On the other hand, if you actually look at today's scenario, it may be somewhat easier to understand this. Okay, he actually introduced this concept of inertia and said that rest and uniform motion are both natural states of an object. Means it may be either at rest or at uniform motion. Uniform motion means continuously going in a straight line without changing the speed. So he keeps on going, it will keep on going. So they are natural. They are natural movements, natural states. Means that you don't need any force to be in that state. However, force is needed only to change that state. If somebody is in rest, to make it move, you need force. If some body is in motion, to change its direction or to stop it or to reduce its speed or to increase its speed, you need force. So, this understanding is hard to come by standing on Earth. It's very hard to figure out. Where Earth's gravity and atmospheric friction force are pretty high. Okay. But if you go to space, so let's look at one scenario where you will be able to appreciate this. Look at this scenario. Okay. So here, you can see very clearly that if you are in space, if you start moving, you will keep on moving. There will be absolutely no force required. In space, people have experienced it. You can keep on moving without any force. And that is the biggest contribution Galileo gave for physics. And he was the one who first started this concept of inertia. And Newton actually starts where Galileo ends his journey. In 1642, Galileo breathes his last in a jail, and in the same year Newton takes birth in 1642, and he takes forward the Galileo's ideas, and we will watch what Newton said and how did he take it forward in the next video. So let's just take stock and see what we have learned. We learned what causes motion. We said force might be the one which actually starts motion, but once something is in motion, you don't need force. That's what we learned today. The next stop for us is Newton's first law and how Newton took forward what Gelileo started. So till then, goodbye. Come back for the next video. Thank you.